So the simplest example probably that I always like to show of this type of the program, it's pretty silly, but anyway. So if you want to check, for example, to make a program that defines whether someone is eligible to get, let's say, driver's license, and if you have the only criterion for that driver's license, it's being, for example, older than 18 years old, you will probably write some sort of program that looks like, I don't know, some if age is greater or equal than 18, then you say that yes, you can have driver's license. So let's return OK. So else, you say no. This program has one internal parameter. If I make this parameter, let's say some age, and I create a separate algorithm that considers data, for example, it takes some database of driver's licenses that were given to different people, and takes, for example, the minimum age of that database. So we take some minimum. We can get 8 equal 18 and set it here. This will be already a machine learning approach. So we have a separate training algorithm. Yes, it's very simple, it's pretty silly, but anyway, this is an example of a training algorithm. And here we have an inference. So what is good in this case is that if we have different states, for example, and there are different rules, we do not need to rewrite our program, but we just need to retrain it on the data that we get. The same applies to everything we do with neural networks from the engineering point of view. So we want to avoid rewriting program. We want to avoid writing some complicated, convoluted rules for that program. We just want to take some raw data, apply a certain algorithm, and extract from there a number of parameters that describe this data and that we can use for our inference. So that's what we do from the engineering point of view. From the mathematician's point of view, that is a bit closer for us, we may look at this a little bit different. We might say that our neural network, that's just a large function that performs something useful, something that we want. And the problem of the training is finding such function among some space of models. So some space of functions that we want to consider. So how does it look like? So here we have some perfect function that does exactly what we want. So whatever we want, it does exactly that thing. What can we do? Well, in many cases, we cannot construct this function explicitly. So we cannot just write some sines, cosines, and just have it. So what do? We take some space of models. So we think, okay, let's consider some functions that are sums of sines and cosines. Or let's consider some more complicated functions. I know, some polynomials, whatever. This is the family of the functions. And we say, among these functions, among these models, we will find the one that is closest to that perfect function. So this is the mathematician's point of view. So we somehow define family of models. We find, between these models, we find the one that is the best, so the closest to the perfect function, and we call this training. After we found it, we can use it for inference. Okay. So here is the same view, just a little bit more enlarged. So here are all the functions in the world, in some abstract sense. Of course, we cannot work with all the functions in the world, so we create some sort of hypothesis set. So these are the functions that we can encode into the computer. Of course, the functions that we can encode, they should satisfy certain conditions. For example, we cannot have some infinite number of parameters in that function or something like that, just because our computer is finite. And among them, we find the function h that is the closest one to the function f that perfectly does the job. Now just a few words, because I'm going into some sort of abstraction in this case. why do we think in terms of functions? Because we all know that neural networks is something very practical. So we give it an image, we get something, some different image somehow warped or something like that. So how does these ideas, how do they relate? And here is an example of that relation. So the first point I want to make, that a large number of problems that we can even think, they may be defined in the frameworks of these sort of functions, so that we have something like input and we get something interesting at the output. For example, the image processing problem may be considered this way. So I have an image, it has certain pixels, size n times m. I can take all these pixels and arrange them into a large vector. This vector has n times m components, so this is the large vector. Then I apply certain function, that is my neural network. I get some new vector and I arrange that back into the image. So for example, this may be some sort of neural network that removes the background. So if I'm on Zoom, I don't want anyone to see what's on the background. This may be the neural network that removes that background. It's not necessarily that you should have from one image another image. So I can have, once again, I can have...
Yeah. Excuse me, I'm sorry, can you make your view on the full screen? It's almost impossible to see anything on the screen.
Full screen.
Can you increase the font?
Thank you. Thank you.
I can use this.
Yes, it's much better because
it's a bit larger. Okay, so here is another example. When I have some input image, I represent that as a vector. I process that with some neural network, but as the output, I get some different vector with a different number of components. And these components can be reinterpreted in a very different manner. For example, I can take triples of numbers and interpret them as points in a space. And I can consider these points as some sort of some joints on the hand. So if we have a hand, we have some image of the hand, neural network processes that and gives you 3D points that correspond to the fingers, to the joints of the hand. And here is an example from my previous lecture. So I didn't want to waste time this time, so I just took the image from that lecture, and here we were testing this sort of neural network, and here you see that it detected the hands pretty well. So we had that sort of demo that time, and I don't remember, that's probably was in the autumn, I guess. So yeah, so this is the case of reinterpreting results of the work of the network. So once again, we have this sort of meaning. So we have some vector, we reinterpret that in a different way. One more example, two neural networks working together. Once again, functional point of view. So I have an image, represent that as vector. My function or my neural network does something with that vector, and we reinterpret that as points that should define a rectangle around some face, and some probability that this is a face. So this way, having some large image, I can extract faces from there. Now a different problem. So here I have extracted this face, maybe somehow warped that to some standard size or something like that. Once again, I reinterpret it as a vector, I apply some neural network, and I get a vector in some abstract space. What's interesting here, this is so-called embedding problem. So I am trying to embed my data that has, in this case, dimensionality m prime times n prime, into some space that has k components. And the neural network can be trained, so we can find such a function that will prescribe to the face of the same person pretty close vectors, while to different persons, different vectors will be prescribed. So just taking some sort of scalar multiplications of the vectors after I have performed the embedding, I can say whether these two photos are photos of the same person or they are photos of different persons. And that may be used, of course, in practice, so as you might guess. Here is once more example from that lecture we had in autumn. So this was our demo that tried to detect well, our co-workers of our institute. The interesting part is that I took photos from our site, from the BITP site. So basically, this network was trying to guess who is who, just basing on one photo. And these photos are often outdated. we don't update them frequently. But anyway, you might see here that at least a few of us were detected and detected correctly as far as I see. So basically, this approach may work as well. And that's not the most powerful neural network that we have. So you might guess that face detection and all that type of processing, that smaller networks may do that very well. Good. Now a little bit more about this sort of point of view, and maybe a little bit more about the detail. So our different machine learning methods, they basically all may be somehow embedded into this sort of framework, and what kind of method we have to deal with depends on how do we answer all these three questions. So the first one, how do we choose the family of these functions? So how do we define them and what do we do? For the neural network, I will show the exact way how do we choose these families, and basically show you that neural network architecture, so that is called by programmers architecture, is basically the way to say how did I choose the family of the functions. The next one, since we are getting to the question that I want some best function, of course we should answer the question, and how do we know this function is good? How do I know that that function is better than this one? So I need some way to compare them, otherwise I can't say that I found something, because what is the criterion of this goodness? And the last way, what is the technical method that allows me to find that best function? So maybe I may have some method to compare them and say, well, this one is better than that one. Function f is better than function g. But if I have no kind of method, some iterative method or something that would allow me to make this function better and better and better, there is no way I can maximize that sort of goodness. So we need that, and I want to briefly get through all these questions, answer them, and we will definitely know what kind of what kind of beast is the neural network. Okay. Good. So this is basically, now I'm trying to answer the first question. So how do we choose the family of the functions which we are working with? So everything started a very long time ago with the idea to mimic the biological neuron. So at that point it was known that neurons, they can get some signals from their dendrites, they can integrate that signals, and at some point they may decide to produce some action potential that will propagate along the axon, and maybe it will make some other neurons to fire or not. Well, that depends. And the simplest model that they could come up with was something like this. So let us consider that all the potentials from the synapses, they are just added up, maybe with some weights. So these are the weights, W0, 1, 2, and then we have some sort of activation function. They added some bias, so this is just some sort of constant, and they said, well, let's make some activation function that will decide whether we fire the action potential along this axon or we don't. Uh, and that will be our mark. What about these functions? Here are examples of functions that are used today. When all these started, mostly sigmoids were used. As for today, as far as I know, ReLU is very often used in the neural networks that I saw. Of course, there are some sort of modifications like leaky ReLU or ELU, but anyway, you can see by these functions that the first attempts, they were something like thresholds. So people were trying to mimic some sort of threshold that neuron fires its potential when it gets more depolarized more than certain threshold. While modern neural networks, they use something like this that looks like, I don't know, if something is less than 0, then make it 0, otherwise just propagate what we have. And they work pretty well. From these neurons, we construct a neural network. So we construct some sort of architecture. We do that by connecting some outputs of neurons to inputs of other neurons. So here is the simplest example of the neural network when I have just a few of the neurons. And these neurons, they get input from the outside. That may be some pixels from the image, that may be some other numbers, so whatever they mean. They propagate the information to the hidden layer. Then this hidden layer, we may have many of them. They propagate it further and further, and at the end of the day, they end up at the output layer from where we get our information. So the processed information that passed through the whole neural network.
And the weight of each signal determines the information. So if we have some image, so this image will be regulated with weight of this signal.
These pixels will come here and will have some number here, number here, number here, just taken from the image. Then each of these neurons performs its internal processing, so it multiplies that by certain weights, maybe performs that sort of ReLU or something, and whatever it has, result is passed to the next neuron or neurons, depending on what is our architecture. It always passes some number, but this number may be 0. So
0 or 1?
It may be intermediate number, as we see from these sort of functions. So you see, they may have almost any value. Well, some functions, of course, they are restricted to, let's say, from 0 to 1 or from -1 to +1. But there is no general restriction on the output, so it may be pretty different. Maybe I'll show some. Maybe I'll show some examples of different connections, and just show a few different layers. The thing is that connecting neurons just one by one may be a little bit too tedious. So we cannot work with individual neurons because modern neural networks, they may have I don't know, some thousands or even millions of these sort of neurons. So we have to do something. And the way to overcome this problem, the problem of too many neurons, is, well, pretty similar to the one we use in different areas of the science. So if we have many very small details and we cannot handle them just because there are too many of them, we just lump them together in some larger component and we operate with that larger component. So if we are doing, I know, some radio technique, we rarely work with some individual transistors or resistors, but we work with some sort of, I know, some microchip or something like that. So we lump everything together, or we just draw that we want, I know, some enhancer somewhere or something like that. In the area of neural networks, we have the same thing. We don't work with individual neurons, but we lump them together into layers, and we operate with layers. So one layer may contain many neurons, and that's a little bit easier to comprehend when they are all collected together. Depending on the connection of these neurons inside the layer, we classify them into certain categories, and there are some that are used, well, pretty often. So I should probably show at least few of them, just with images, to get some idea. For example, if my neurons are all connected, have connections to all the neurons of the next layer, we will call this layer fully connected. Well, pretty reasonable, fully connected, because all connections that are possible, they are here. So if it gets some information from wherever it gets, it may be some outside world. So if this is some input layer, it may be some different layer of neurons if this part is inside, hidden inside of the neural network. It will process that, and it will then send this information to all the neurons of the next layer, and we call that fully connected. One more example, very often used, especially in the area of image processing. This is so-called convolutional layer. It looks a bit different because this is the way to better comprehend what is happening. If we consider all the neurons of the previous layer, we think of them as some sort of arranged in a rectangular matrix. We take results of their processing, so these numbers, we multiply them by certain weights, and we take them to the output. So we add everything together and we set it in here. And with this is called convolutional layer. It's in some sense it's similar to the convolution we are used in physics. Yes, we use some sort of integral, so we integrate with some kernel. This thing is also called a kernel, but that is some sort of discrete case of the convolution, and of course we should use some finite kernel because we work with finite computers. What is interesting, just as sort of fun fact, we have something pretty similar in our eyes, because if we look at the retina in our eyes, the photoreceptors, they are not just standing alone, but they are collected into some sort of things called receptive fields, and these receptive fields, it has a receptive field center that is connected to the bipolar cell, and it has some periphery of that receptive field that is connected to the horizontal cell. And the thing is that when light gets here, we get some result that is pretty similar to what we get with convolution. So if we have a high signal both on the periphery and in the center of the field, we get much lower output from this cell that gets to our brain than if we have, let's say, low signal in center and high signal on the periphery. Well, there are different kinds of these receptive fields and so on, but the general idea is like this one. So if we have some gradient, we will get, in most cases, we will get much stronger signal than if we have no gradient. So we are more feeling gradients than exact colors or something like that. And that's often demonstrated with these sort of demo. I'm afraid who's in Zoom cannot see that well. But I can show this effect right here. If you see this sort of figure, I think you can clearly see that the upper part is much darker than the lower part. But if I go here and I somehow hide this part of the image, well, you start seeing that these parts are pretty similar in color. So if I somehow hide this part from here to here, we will see that this gray and this gray, they are exactly the same. Why? Because we are reacting basically to gradients. We have something similar to the convolutional operation. One more layer called max-pooling layer. This is the layer that just takes part of the inputs. So once again, you can think of this as some individual neurons that have produced some numbers. So here are some exemplary numbers, and they take these numbers in blocks and calculate, for example, the maximum value of these numbers. So if I have some previous layer, I can remove part of the information and propagate only the information that corresponds to the largest numbers in certain areas. So here we have the result. So that's max pooling layer. There are a few more. I guess I will skip them. Just you may just notice that we may have self-referring layers that are used in recurrent neural networks or RNNs that may produce some result to the output and some result that will be fed back again into this layer. So this way they create some sort of memory. These neural networks were first used before we had transformers, all that ChatGPT and other powerful networks. These were the first attempts to get something that can answer our questions or somehow process the text. So it was performed on RNNs, or a little bit later we got so-called LSTM, so long short-term memory. Anyway, batch normalization layer, a bit of formulas, but the only thing I want you to pay attention that in some cases we have that numbers that we propagate through the neural network, they get a little bit out of control. So sometimes we insert layers that will put them in the range. So this layer, it tries to make all the data that passes look like normal distribution. So if I feed many images into the neural network, at some point I extract some data from the internal layer, and this layer is collecting information on the mean value, on the dispersion, on the variation of the data, and then normalizes that. So it will divide some number, it will subtract the mean value just to make it look a little bit more closer to the Gaussian distribution. Dropout layer, that's just for training, so sometimes we block part of the neurons from training to force them all to learn. So it may happen that some neurons become much more useful than other neurons when we train the neural network. Of course, we don't want to carry some large neural network where only 10% of neurons are useful. So sometimes during training we block some of them and we force others to learn. So everyone should learn. Here is an example of the simplest neural network, and probably historically the first one. This is a LINET. This neural network is already capable of seeing some numbers and deciphering what kind of handwritten number do we have. And these are examples. So here we have convolutional layers, one convolutional layer. So the raw image comes in here. Convolution is performed. We get another convolutional layer, max pooling layer, convolutional layer, max pooling, fully connected, and so-called softmax that takes that numbers and puts them into the range from 0 to 1 to make 10 different channels. Each of them describes a probability that we have, that the network have seen that exact digit from 0 to 9. So that's basically we have moved through all the layers, and we have constructed some network from that layers. Architectures may be wildly different. So here are some examples. I'm not getting into them. Just want you to see that modern neural networks, they are pretty large. So even pretty old VGG has 138 million of parameters. So these are enormously large networks, and any of them may be thought as some sort of function that was constructed from that very simple functions when we are adding something and we are applying that activation function and just connecting them in appropriate manner. So this is basically how do we create that family of the functions that we will be working with. Here is a more practical example. So I mostly use so-called PyTorch framework that allows me to create that sort of layers and connect them, some inputs to outputs. And here are some names in the PyTorch that are used in practice. Here are names that basically we used when considering this presentation. So once again, all these layers we have just seen, and that's basically how they are mimicked in that framework and how you can call them if you need to create any of them and connect some data. Good. So we have created some neural network. So we have constructed some architecture. We have something. Now the second question is, okay, I created some network. I need somehow to learn it. So because if it just created from scratch, that's some random function, and it's pretty obvious it will not do anything useful for us. So for starter, I have to know some way to say whether it does what I want or it doesn't. And of course, we cannot just satisfy with some sort of binary classification, it does or it does not. We have to measure that in some quantitative manner to get some number. And here are just a few examples, because this sort of measurement, or how good is it, that depends on what this neural network does. So if it will do something connected to physics, we will have to somehow include into there our knowledge of physics. So whether the results of the neural network, some predicting maybe some physical process or something like that, whether this result is good, we can say only if we know physics and we can distinguish these predictions and say, well, this is good prediction, that prediction is not so good. Here are just some simple examples. So the first one, that's example with images. We may have a neural network that tries detecting birds. And as in the case with faces, we had some sort of neural network that generated numbers that we may reinterpret as the rectangle around our object of interest. Here we have the same example, but here we have a result of one neural network working, so this red rectangle, and another neural network working, this blue rectangle. So which one is better? And one of the ways to compare them is so-called IOU, so intersection over union. So we have some area of intersection, we have some area of union, we divide them, and we get some number. Well, this is a pretty reasonable metric. If we have some perfect coincidence, for example, I definitely know what kind of rectangle do I want, and I know what neural network generated. If they perfectly coincide, I will have 1, because I have intersection equal to the union, and that's it. If the neural network is absolutely off, I have no intersection, 0 intersection, so I will get 0. So some pretty reasonable measurement. Here is another example. If we have some sort of multi-class classification, we can try to crack parameters like precision and recall. Once again, not diving into the details, I just want to say that we have some statistical measurements of whether our predictions of certain classes in the classification problem are more good or, let's say, less good. So if I will show to the neural network some bunch of images and I will ask it to detect, I don't know, cats on that images, and then it will provide me, so these images, they have cats, that images, they don't have cats. I can calculate these sort of parameters like precision and recall, so how many images with cats were actually selected with the neural network. So there were 100 images with cats, so how many did it catch? So did it find 80 of them, 90 of them? So that will be my recall. While precision will tell me, if neural network tells me this is the image of the cat, what is the probability that there's actually a cat in that image? So maybe it made some mistake, and that's a dog. Another example that's maybe so-called R-squared. This is very often used metric if we have some sort of regression problem, so neural networks, they are capable of that as well. And another example of a pretty specific way to estimate whether the network is okay or not. This is the so-called autoencoder. So I feed some data to the input, it goes through the network and returns on the output. And the goodness of this network, I require that the information on the output is the same as the information on the input. It may look a little bit strange, why do I need all of these if at the end of the day I get the same thing that I had on the on the input. But the thing is that these layers, they are shrinking. So they become smaller and smaller and smaller. And here I have some sort of bottleneck. And it may happen that I feed in here, I know, some million of numbers, while in the bottleneck I have 100 of numbers. And if the initial information can be fully recovered with that sort 100 of numbers, this is a good sign that that initial information is, in some sense, there's too much some noise or some redundant information. So we can compress that in the much lower dimensionality, and it may be much easier to work with that low dimensionality than with some sort of high dimensionality. So many algorithms, they will start working much better and much faster, and they will become much more even robust. Because if we lose something in here, that will be most probable that will be some noise. So not some actual data, but some noise, and we can even perform some sort of noise reduction. So that's really cool for some experimental data when we have some noises and we want to get rid of them. Okay. Now we have a way to get a number that describes whether our neural network is good or not. Now we have to perform some sort of optimization. So once again, I just get very briefly through all this stuff. So when we have that network, we have that number. So getting that number, that's basically calculation of so-called loss function. So we call that some loss function or some cost function. And now we want to minimize that. So basically, once again, we look at our neural network together with the function that estimates how good is the output as one large function, and we want just to minimize this function. So how can we do that? Many methods are available, so here are just a few classes of them, so optimization methods. I divide them by the order, like 0, first and second order, and the order basically describes what is the maximal order of the derivative that is used by this method. In neural networks, almost exclusively first order methods are used. So zero order methods, they do not need a derivative, but they are not used. We use first order methods and we can get derivative in neural networks. I will show maybe the mechanism how do we do that. While the second order methods, they may be cool, but they require too large, they consume too much memory. The thing is that for the first order method, we need the same number of parameters for our derivatives as we have parameters in our neural network. So if I have 1 million parameters, I will need 1 million derivatives. But if I have the second order method, that will be the full matrix of Hess, so Hessian matrix, and that Hessian matrix, as you might guess, for 1 million parameters, that will be 1 million times 1 million. So that's already a very large number. So we don't want that. Available methods are pretty different, so they almost all stem from so-called standard gradient descent, basically created, I guess, by Lagrange or something, or someone like that. And we have different modification of this method. You may see here I have even some modifications from 2018. Maybe we have even some more modern methods. I should say I didn't check that, but there are a lot of different methods. And here is an example of these methods working. So why do we need so many of them? Because they work pretty different. So here is an example, some random function that we will try to find some minimum. And now I'll start. So here are how these methods progress. So here you see different tracks. You might guess that these methods are iterative, so they perform some iterations, and at each step they are trying to get to the minimum of the function. So here you see they all started at one point, but they ended up in very different points. One of them were able to find the global minimum. I guess that was Adam, so these one, red line. Well, the rest, they were stuck in some sort of local minimum. I guess if I put it like this, you can see a lot of local minima of this function, and some of the methods, they were stuck in that local minimum. So that may happen. Not always neural network trains to the best results, so sometimes it may be stuck somewhere in the middle, so that may happen. Okay, for these methods, we need gradients. For gradients, we need a derivative. So maybe I'll try just very briefly get through these sort of examples. So how do we get derivatives in neural networks? That's the process that is called backpropagation. I will show that with this sort of example. Here are the neurons. They are, I don't know, I just came up with some random functions, connected some outputs to inputs, just to show an example. So I'm not sure if that is useful for anything. So what do we have here? So we have a bunch of inputs. So this is some data that is fit from the external world. Here we have some input layer, some hidden layer, some output layer, and here is the loss function that estimates whether this result is good or not. For any function in these neurons, we know the function, so basically what this neuron does, and we know all the partial derivatives with respect to the parameters of this neuron. So each neuron has some internal parameters, some weights, and we have partial derivatives with respect to that weights. What do we do now? Here I remove some unnecessary derivatives. These are with respect to the input values, so we can fix input values. We have what we have. The next step, what do we do now? We initialize parameters. So we need to start our neural network somehow. Most cases, they start with some random initial parameters, and then we just hope that it will converge to something reasonable. So I will initialize them with some sort of random numbers. What then? The phase called forward propagation. So I get some data from the external world. So these are some numbers that came to me. That may be, I don't know, some pixels of the image reinterpreted is in this way or whatever it is. What do I do? Well, these numbers, I can set it into all these functions and all these derivatives and basically calculate the values. So since I have input, of course, I can calculate values of my function. I can get the output. When I have the output, I can pass that output to the next layer because I have already calculated all these neurons. Now I can pass information to the next layer to these neurons. Now these neurons, they have input. Since they have input, they can calculate the output together with the derivatives and pass information forward. Now information is passed forward, and here we have some sort of value for our loss function. Now
But coordinates are different. The first neural network is coordinates U1 and U2, second U1.
Yes, because we have different parameters in these neurons. Let me show it here. So here we had some function with parameters U1 and U2 and some input values. So here we have partial derivatives with respect to the parameters of this neuron. So each neuron knows partial derivatives with respect to his own parameters. The beauty of the process is that he doesn't need to know anything about all the neurons around. He just needs to calculate his own derivatives with respect to his own parameters, and that's it. So this one will have his own parameter, this one, and so on. So they don't know anything about each other. And basically, that's pretty enough to calculate the result. So whenever I have, I don't know, some cosine of x, I don't actually care where did this x come from. So this x may be result, I don't know, of some polynomial. So it may be some y squared, which is now x, but I don't care. I take the cosine as usual. The same thing is here. So they don't care about each other. They just take what they have on the input and they calculate the output value. The real magic starts on the backward propagation. That's basically a clever use of the chain rules when we get derivatives. So we have the chain rule, and that's the example how to use the chain rule to get something interesting. So now each neuron, after I have propagated the information, it knows its value and it knows basically its partial derivatives with respect to its parameters. But now I have to make a gradient descent step. So I need a gradient of the function, of the loss function, with respect to parameters of each neuron. And these may look a little bit complicated, because how do I find it if the function is here and my parameters are somewhere here? And here where the chain rule is coming into an action. So let's start with the simpler thing. So let's consider the last layer. So here I have result of the function, here I have the last layer. So if I need the values of the partial derivatives with respect to parameters of the last layer, I basically already have them. So when information was propagated forward, this neuron has calculated that values, so I already have them, and I can plug them into the gradient. So this is the easy part. So these basically I already have. I can just plug them in. Now the problem starts, because now I need derivatives of the function with respect to parameters in this layer. But how do I get them? I can just use these numbers. These are not derivatives of the function. They are derivatives of these neurons. So here I perform back propagation, and basically I use this sort of chain rule. So if I have one neuron feeding data into another neuron, and here I have some sort of result. As always, we look at that function. So here is some function f, here is some function g, here I have some input, let's say x. This is basically f of g of x. So if I would like some partial derivative with respect, I don't know, some internal parameter of function g, let's call it, I don't know, some v. So I want df over dv. I don't have it, but I can use the chain rule. I can have something like df over dg, like, and dg over dv, so something like that. So, and now df over dg, you see that g is basically input in the function f. So this part is already known. It's already calculated. If I extract it and look somewhere on the side, I just have some function, it has some input, it has some output, and that's it. And if I know the function, of course I have this sort of derivative with respect to its input. So we already have that. So this part we already have. But we need this thing. So what do? We take this part that we have from the layer and we return it to the previous neuron. So that's by back propagation. So we propagate this thing, we propagate back. We turn it back to this neuron. Now this neuron, this is G, and it knows his own derivative. It has no problem. And now, from the next layer, it acquired this derivative. So there is no problem to multiply them. It's just simple multiplication of numbers. So we have calculated this thing, back propagated, we have this thing, we just multiply them, and that's it. And here is the mechanism. So here you see these derivatives. These are derivatives with respect to inputs. So derivatives with respect to parameters of the last layer we have already used. They are now set in our gradient. These are derivatives with respect to inputs, and we backpropagate them. So I just share this information with the previous layer. And now that is enough to perform multiplication. So now I have multiplied these partial derivatives, and I say I use chain rule, and now I have derivative of my function with respect to parameters of these neurons. So I can plug them in into the gradient. So here I have some more numbers. And the beauty of this procedure is that I can pull the trick over and over and over again. I can send my data once again back. I can multiply. I can plug them in. I can get the gradient. So this is the backpropagation. And that's basically the mechanism that is behind learning all the neural networks. And I guess it was one of the reasons behind Nobel Prize just a few years ago. So I guess
this is Boltzmann backpropagation.
no, that's Boltzmann machines. They study a little bit different. So it's yes, that is a method of creating neural network, but it's a bit different from the backpropagation we have here. But I guess it was included in the statement of Nobel Prize. Well, I may be missing something, but I thought that it was. Here's once again the same scheme, just a little bit more simplified. So here is one neuron operation. So it takes some inputs, does something, produces an output. That's forward propagation. On the back propagation, it gets from the next layer derivative. It has its local gradients, performs multiplication, and sends everything back. So that's one neuron back propagation, and if neuron shares information with few other neurons, it just adds up whatever he gets back. Everything comes up from the chain rule, just simple derivatives. Good. I think I'm 2 minutes behind the schedule, but I have just a few things to show, and I think they make me look maybe more interesting. So let's try constructing some very simple neural network that does at least something, and I will just try to show a little bit hands-on how that is performed in the Python language with the PyTorch. So now I'm trying to get the data set, probably the simplest data set we can work with, that's so-called NIST. That's a database of the hand-drawn digits. So here you see them. These are just small pictures, I guess 8 by 8. So some hand-drawn digits, they were transformed into the black and white and basically squeezed into these sort of squares. And we will try to detect some number basing on how it's drawn. So here is our data set that we have. This is our so-called ground truth. So we know what is drawn here. And now we want a neural network to train, to distinguish between these numbers and tell us what is the number.
So red, this is correct.
Yes, red is the correct value that we expect from the neural network. So if I feed it this sort of image, I will expect 6. If this one, I will expect 7. So that's what we consider to be the truth. And here is the simplest neural network I was able to come up with. I called it RandNet because I just lumped together a few pretty random layers. But anyway, so here you can see its architecture. So here I am creating some convolutional layer. I'm setting some number of input channels, some number of output channels, size of the kernel, 3 by 3. So I will convolve with that small square, 3 by 3, and so on, some different parameters. So here I have average pooling. It is similar to the max pooling layer I showed, just I don't take the maximum number, but the mean value. And then I use flatten to does basically nothing, just changes the shape from the rectangle to some long vector. And then it is called linear in PyTorch, but basically we call this layer fully connected. So it takes all the inputs and generates us some numbers. So let me start this part of the code. So here we see once again this architecture. So information will be propagated through convolutional, average pooling, and linear layers. So here you see the number of parameters of these layers. So we have some parameters for the convolutional layer. That's basically that kernels 3 by 3, some number of them. Average pooling, it just calculates some average. It does not have any trainable parameters. Flattening just changes the shape, so no trainable parameters. And linear, well, it has a lot of parameters because that's basically fully connected layer. And all these parameters, they have to be trained. What do we use? Okay, so now I have created an architecture. What have I basically done? I have defined a family of functions among which I will search for the best function. So I have performed my first step. So we create neural network as the architecture of the neural network as basically defining family of functions, and I have just done it. Now what I need somehow to estimate how good is my neural network. How will I do that? I have my images together with labels that I consider to be correct. So I want to use this information. So I will feed image into the neural network. It will get me something, and from that something, I want to collect all that information and say these neural networks works very well, and that one does not. So I use so-called categorical cross entropy, often used, let's say, metric in the case when we are trying to assess multi-class classification. So this is just a way to get all the data from the network and collect it into one number that will tell me how good or how bad is my neural network.
Can you tell in brief what is T and what is sigma?
One moment. T, that should be from ground truth, I guess. It is 1 if the label I is the real label, and 0 if they do not coincide. Sigma is the result generated by the neural network. So the last layer of the neural network, we perform this sort of operation. As you see, the neural network generates some number. It can be from plus to minus infinity. But we want some more reasonable numbers that can be reinterpreted. So if Z is the output of the neural network, we have 10 of them, 10 of these, and we calculate from them sigmas. What do these sigmas do? If Z is very negative number, so it's very, very negative, e to the Z will be close to 0. So I will have this sigma close to 0. If Z is some large number, I am dividing by this sum. So I'm basically warranting that all these sigmas will sum up to 1. So I can treat them as probabilities that the result I have is certain digit. So let me show it this way. So what I will get from the neural network, I will get some 10 numbers. Each of these numbers will correspond to one of the digits. So that this is digit 0, this is digit 1, 2, 3, and so on. So, and whatever I get from neural network here will be reinterpreted as a probability. Let's say if it says 0.9, it means that this digit 0, has 90% probability that neural network has seen it. So here I have my neural network. Here is my image. I have drawn, I don't know, something, let's say like this, feed it into neural network, and it gives me this sort of result. So if it says 0.1, so 90% it is 0. If it says 0, it means that this is digit 1, 0%. If here is, let's say 9, it tells me 0.1. It means that this is digit 9 with the probability of 10%. So I draw something in between 0 and 9, so it tells me, well, it's 90% chance that this is 0, and 10% chance that I meant number 9. And these numbers, since I get from the raw neural network anything from minus infinity to plus infinity, I first use this function. So I say that these are my sigmas. So this is my sigma 0, this is my sigma 1, and so on. And they are basically calculated at sigma I is equal e to the vi. This is the output of the neural network, just raw output. If it's minus something big, I get 0 here, so it's this case. And it is normalized by dividing on the sum of all such, say, e to the dj. So these warranties that whatever number I get here, if I sum them up, I get 1, which is pretty reasonable as we work with probabilities, and we expect that the total probability is always 1. So always some number is drawn, always particle can be found somewhere, and so on. So this is the case. And on these numbers, on these sigmas, I use later this function that basically describes me how good this neural network worked. So if my neural network guessed correctly, so sigma, so all ti's, they are 0 except the one that is the correct class. Let's say it was, I know, it was 0. So t0 is equal to 1. The rest are zeros. So this sum is basically reduced to t0 times logarithm sigma 0. So this t0 will be equal to 1. So everything is basically reduced to logarithm sigma 0, but minus sign. Minus sign that we have here before this sum. So now what does it mean? If this sigma 0 is close to 1, so my neural network correctly guessed what we have, I will have some number close to 0. If this sigma 0 is low, so it didn't guess, it made its bet on some different digit, this number will be negative, maybe strongly negative, because we have logarithm. So it goes somewhere down. So I have some strongly negative number. With this minus, it becomes strongly positive, which means that if I am performing some minimization procedure, I will strongly want to get away from that point, because we have our loss function and we want somehow to minimize it. So if I didn't guess, I get some large positive value, so I'm high here. If I guessed, I'm somewhere low here, near 0. Probably I have draw this. So that's the case. So now whatever I need to do is just minimize this function, and I will get some result. So I will somehow work with that parameters, and we will get something. So let's do it. Here is example how we do that in Python. It will train for just a brief moment. So here is cross-entropy loss. That's basically that function with logarithms and so on. Ada minimizer, so the one that we have seen in previous slides, the best one that was able to find that global minimum. So I use it. Learning rate, just internal parameter of that optimizer. And here we perform training. So I have some number of epochs, so number of steps that I am committed to perform to get that minimum value. Here we have our model, so I extract some data from that model. I calculate the loss function. That's basically my cross entropy. Here I call the function loss backward. That's basically that procedure I showed you with that chain rule and so on, propagating all that partial derivatives, so that's it. Here I perform optimizer step, which means it takes the gradient that was calculated on the backward step and calculates the next point to try. So we were on xi, here we will be on the xi plus 1. And this is just some internal data that we can print out here and see how it goes. So here we see that our loss was diminished a little bit, so we started at 2, we ended up at 147. So something has clicked. Not bad. Now let's try evaluation. Why not? Yes. So I will not go into the code. I will just show you this sort of picture. So this is so-called confusion matrix. This matrix shows us how good is this neural network, but in a way that is more accessible to us as humans, because loss function is great, but that numbers, they will not tell me much. This one will do. So this is the true label that the image had. This is the label that was predicted by the neural network. So I take some image, for example, of digit 5. I ask neural network, predict me, what is this image? And if neural network tells me it's 5, it goes into these squares, so I add plus 1 in here. If it tells me that it's 8, I'll add plus 1 in here. And at the end of the day, if I process all the images I have, I will get this sort of matrix. It shows that it works pretty reasonably. So perfect matrix should be, of course, diagonal. So that's the case when the true label and the predicted label, they perfectly coincide. In this case, we see it's almost diagonal. So there are few cases when our neural network missed something, but in most cases, it works really reasonably. So now just to show you some internals. So once again, reiterate what we do. These are basically the last 2 slides. But I want to just go through them. Here is an example of what happens in that neural network. So once again, we are trying to decompose that and look at it as some functions. So here's my input. I guess it should be number 4. Not very well seen, but well, these are images 8 by 8, and that's it. So the first layer is convolution. So I take some kernel. This kernel was learned during that training process, and I convolve it with that kernel. We have a few different channels on the outputs. Each channel is this image convolved with a different kernel. They all are 3 by 3, but they contain different parameters. So I have convolved with these, and so on and so on. So here I have my outputs. Then I perform average pooling. So I take squares 2 by 2, I take average, and I put it into the appropriate position. So here you see that if I had here 8 by 8, something 8 by 8, here I have something 4 by 4, because I have averaged certain pixels. Now I use this thing, I feed them into the linear layer, so I don't show that linear layer here, but after that layer is processed and after we use this sort of sigma function, we will get something like this. So these are basically the probabilities that we have, digit 0, digit 1, digit 2, and so on. Here you see that our neural network is very certain, this is digit 4. So it basically predicts this digit. So these are these sigmas. Let's check some another image. So here is digit 5. Let's maybe find something it's not so sure. It's almost always yes correct. Well,
We can recognize.
There are only few non-zeros of that.
Uh-huh. Well, here's one. I found it. I really tried and I found it. So this digit, probably we can recognize that as 7, but you see that neural network gives also some credit to the 9. So it thinks that maybe we just didn't close the loop here, and that with very small probability, it could have been 9. Good, so here's what it sees. And the last demo for today. So we use images from the database. That's pretty good, but why don't we try drawing them by hand? So let me try draw something and pass to that neural network. So here I'm trying to draw number 5. So here my engine has cut out this part of the image, transformed that into 8 by 8 16 grayscale. So that's the expected input of the neural network. And let's try to ask it recognize, and it recognizes that as 5. So which is pretty reasonable. It does not always work, so probably if I try to draw something else, it may not recognize, but let's try. Here it makes a mistake, so I draw 9, but it recognizes that as 5. So depending on how I draw that, it may be. So maybe this sort of number was, I don't know, too low number of 9s in the data set. Or maybe my conversion wasn't able to reproduce that exact view from the data set. So here is basically an example what happens if our data set is in some sense incomplete, or we are trying to use some data that
Maybe
is...
there is no difference between up and down. And that's why...
Hard to say. I mostly think that in the data set, if we look in here, all the numbers, they look a little bit different. So, so numbers 9, you see them like with this one or this one, so they may be pretty different from what I have drawn. So hard to say. But anyway, yes, these things may happen, and that's pretty okay. So in these cases, we just need to expand our data sets and basically train it on something more hand-drawn in my engine than on the raw NIST. Good. I guess with that being said, we can conclude the first part. So we have considered our example. So let's take a break.
Okay, dear colleagues, maybe questions? Are there any questions? In Zoom, maybe here. There are so many information for us.
It's just,
Yeah.
it's very interesting. Just about the optimizers, so they all are based on the gradients, right?
Yes, absolutely.
They are just inside, there are some adaptive algorithm which tries to find them the best way, or is there some way how they try actively to, let's say, chop out of the local minimum, or do you know what's...
Well, basically all the optimizers we can use, they can rely only on, let's say, local information. Because we are working with a very high dimensional spaces, we cannot afford even tabulate that function with some reasonable number of points. So we can rely just on some locality. So what does the local environment give us? It's just the value of the function in this point and gradient. Taking some higher derivative that causes problems with memory, so that's all we have. But these algorithms, they are pretty clever. For example, they use some previous history. So everything started with, I guess, Nesterov momentum. So when instead of just simple stepping from the gradient, so if we have some function, we see that the gradient goes here, so we want to make step there. But they started adapting the size of the step and even direction based on the previous history. So they may be pretty clever. I don't have a formula here, but in a different presentation, I guess I have even exact formula how do they do that. And they mostly look like something, I guess some sort of filtering. So some previous steps, they are collected into some parameter, and that parameter is used when predicting how much do we want to step according to some direction. There may be even more clever algorithms that are trying to estimate. Well, the thing is that what we minimize is basically not the function itself, but some sort of approximation of that function. So we have some model of that function, and we are trying to deal with that model. So if we interpolate that function with some sort of second order function, we can immediately step to the minimum of that function and try what's going on there. And there are some algorithms that even try to estimate how good are our predictions and make some sort of range in which we work. So I can think of this function as interpolated with some sort of second order polynomial, but not further than certain distance. And this distance interactively changes when we move. So it may become larger or smaller depending how good do we guess its value. So if we guessed well, we make it larger. If we guess not so well, we make it smaller.
Thank you. Thank you. Maybe other questions? Yeah.
I have a simple question. Are there any randomization schemes used in this AI? Random number generator.
The first thing that comes to my mind is basically stochastic gradient descent. So in some cases, yes, minimization procedures, they can use some stochastic methods like stochastic gradient descent, SGD, and I even heard often that many people have it as the first choice when they are minimizing any neural network. So it has to do with some random choosing of the samples for the comparing for ground truths or for learning. And as far as I heard, it's pretty good and reasonable method. Yes?
I don't know if we still have time.
Yeah.
I mean, I read related to this when I was discussing our machine learning attempts. So we will ask how do we initialize the coefficient, and then this person said he's working in machine learning at this level, and he was saying that yeah, we do run several initial configurations or initial values of the parameters, and they might be randomized, right?
Yes, yes, it's absolutely.
At the initial condition, we might have.
Yes, absolutely correct. Yeah, so when we initialize neural network, that's a pretty separate option. So we may use some random parameters, or there are even methods. I don't remember their names, so I'll be honest. But there are a few different methods how to initialize neural networks, and they include often some randomness into the choosing of the parameters.
Okay, dear colleagues, we have half an hour to the break. Vitalii, how many time do you need to
for the second part?
Because we need to have some break, and after that we have a lecture.
Well, I'll try to put that into 25 minutes. Maybe I'll skip some parts, but...
Okay, so probably we can continue, and after that we will have a break. So.
Okay, let's do it. I'll try to make it quick, maybe more focusing on some examples. Okay. So this part of the lecture I want to devote to some, let's say, problem that we can solve with neural networks, but that is as much close to physics as I can. So let's try solving some cases of Schrödinger equation with neural networks and compare that to some sort of traditional methods like split operator method. So here is our equation. I have set h bar equal to m equal to 1 just to not bother with all that coefficients. And here we have certain potential and first kinetic energy. So we will consider a few different problems and try to look what do we get out of it. I will show a few demos. Well, the first one. Okay, before we get to the first one, so what is basically the challenge? So the challenge in most cases is predicting quantum state psi at some time moment t and certain coordinate x. And the problem is that numerical methods, they mostly have to evolve from time equals 0 to the time we are interested in. So we cannot skip anything, and we have to calculate every intermediate microstate. And that's not good because, of course, it's time consuming. We have to have many microstates. We cannot make our steps too large because that causes problems. So we have so-called current Friedrich-Levy condition that forces the time step to be microscopically small, so we can't just skip too much. We have, of course, error accumulation, and we have massive complexity that highly depends on the dimensionality of the space. So I'll be showing today some one-dimensional examples. They are simple, they are quick, but if we get into 2 or 3 dimensions, that's massive, and probably we wouldn't be able to wait until that calculation ends. So what do I want to show? So first of all, I will show some classical methods because we need some ground truths to know what can we do without any neural network, to be able to compare that to what we can do with neural network. So after I show what here happens, we will move to so-called physics-informed neural networks. They are not so good as I expected, but anyway, I was able to make some demos, so we will try to make that psi function with physics-informed neural network. Then we will consider the problem when these networks are really useful. So this is inverse tomography. And we, instead of finding our psi function, we will try to retrieve the potential. So that's a really interesting problem as well. And at the end, I will show some operator learning. So we will return once again to finding the psi function, but this time I will use a method that gives some result. Good. So let's get quickly through, and I will start some demos just. Okay, so what's the main problem? So suppose we have some simple potential and we have a particle in that potential. If we want to calculate our psi function, we need so-called time evolution operator. That looks something like this. So we have e to the minus I, h bar is equal to 1, so Hamiltonian delta t. What is the main problem? There are basically 2 problems. The one is that our operator t, so our kinetic energy, is non-local operator, so that's a problem. And the second one, that we cannot just split them apart because our commutator is not 0. What can we do? Since we cannot just simply write that it's one exponent times the other exponent, that will simply not work. We have to come up with something. In many cases, we come up with some sort of sums of something and so on. But in this case, we will make some approximation. This is Trotter-Suzuki decomposition. This is an approximation of this exponent. And it turns out that I can write it as exponent in let's say, in this coordinate space, but half of the time, times exponent in the momentum space all the time, all the delta t, times once again exponent in the coordinate space, but half of the time. And it turns out that multiplication of these 3 things is pretty close to the real operator that we have here. It's so close that it's O to the delta of the t cubed. So not even squared, but t cubed. That's great news, because when we perform integration, we will lose one from here, and we will get some global error of the order t squared. Okay. So what will our method do? I will show you a demo just in a moment, just explain what it does. So here we have these sort of operators, and we basically just have to apply them to the psi function that we get to basically evolve it that delta t. So I should just multiply that by this exponent. Then I need to multiply it by exponent in the momentum space. So this one. It's not so easy because t is non-local, but I can use Fourier transformation to jump to the momentum space. In the momentum space, this thing will be just a multiplication, so it's just nothing. So I skip to the momentum space through the fast Fourier transform, so f of t stands for the fast Fourier transform. I perform just multiplication by this thing, so it's easy. But now I'm in momentum space, so I perform inverse fast Fourier transform. I get back into the coordinate space, and I multiply by the last exponent. And basically, this thing gives me the approximation for the quantum state. Well, I'll skip this part. That's just the code that performs everything. I don't think we need that. But I'll show you a demo. That's, I guess, much more fun. I hope you can see this is the potential. It's not very well seen here. So here is the small Gaussian right here, and here you see the wave packet that is propagating. I have some dampers on the sides. Once again, too bad seen, but here are different colors that show these dampers. I need them because I use Fourier transform. Whenever I Fourier transform something, I get the topology of the cylinder. That's inevitable. Just because I'm working with the finite computer, my Fourier transform always will be finite. And any finite Fourier transform, it just locks anything to the cylinder. Okay, let's try something else. Let me make the value of k smaller, so I make smaller momentum. Here we see this wave packet propagating, and we see that part of this packet tunnels through the barrier, the other part gets back. So we have some transmission, we have some reflection. We can edit this potential a little bit, so maybe let me draw it by hand. I don't know, let's draw something like this. And here we have, once again, our packet is propagating. This potential is too large, so it's basically nothing is transmitted. But if I add some more momentum, so let me add some more momentum. So here it gets to one thing, here is the potential well, it gets to that well and propagates to the right. So depending on the parameters, we can say how our particle will move and what will be the psi function. So I have some psi 0, that's just some packet with the normal distribution, and here we see how it propagates along with, well, maybe just some last neat demonstration. Let's make it infinite well, and I don't know, some high momentum. So once again, it's not clearly seen here, but here starts the potential, very, very large potential. Maybe it's better seen here, so here we have some large potential, here we have some large potential, and here is basically nothing. And the particle does not get to the dampening zone, so it does not influence. And here you see how this packet just bounces here and forth, back and forth in this potential well. It spreads, and if we wait long enough, it will collect once again back, and so on. So here's basically the nice picture of the classical method that we can use to produce some estimation for the wave function. Throughout the demonstration, I will use this method as some sort of ground truth. So we will compare what we get with this method, and well, maybe get some idea how good is what we think. The main problem of this method is time that we need. So this is just a small estimatory table. So we are working with 1D for this presentation. That's because it's very quick, so I can make a lot of steps. So there is no problem. In a second, I can calculate propagation of the package far, far in the future. If we were working in 3D, that 1 second would transform into 18 hours. So we will have no ability to do something with that. So basically, our main motivation to switch to something different, to some neural networks, to some other methods, is time. We don't want to wait so long. So we want something better. One of the ideas I tried, that's so-called physics-informed neural network. The idea is as follows. So we are training neural networks on some data, and at some point someone says, well, if this data comes from physics experiment and we are getting some results that should be physical, why don't we include our knowledge of physics into that training process? So why don't we demand from neural network and say that results should have certain symmetry, or certain parameters, something should be conserved, like energy should be conserved, or momentum should be conserved, and so on. And at some point, people get even to the point when they say, well, in some cases, I don't even need any data set. My physical restrictions are enough to train the neural network, so to make it produce some reasonable result. And in this case, I tried basically simulate that. So we know our governing equation, we know the Schrödinger equation, and here I tried so-called zero to train this network to predict psi function when I give it some timestamp t. This example is a bit useless, so probably I will not stop on it for a very long time. Just mentioning that in other cases spins are still useful, so they can perform some reconstruction of velocity and pressure, they can solve some Econol equations, or some electronic equations are used in medical imaging and even in plasma physics, so there are many areas they are used. This one is a little bit silly, but anyway. So I get some neural network. This neural network I feed in x and t, and I expect some results. So psi function that contains real part and some complex, some imaginary part. And since the neural network inherently supports derivatives, I can always get derivatives from here, and I can use them in the Schrödinger's equation to get something more or less reasonable. Well, here is my loss function. These are basically some residuals from Schrödinger equation, some initial conditions, so psi 0, some boundary conditions, and so on. Maybe I'll skip all these technical part. I have solved some problems when getting through all of these. It often gets me just 0 of the output, so I had to move from UV, I had to move few parameters like R and S, so on and so forth. But let me show just training. This was the procedure of training. It will start, but I guess starts too long. Root. And I'll show the video of that process. So it took me something like 12 hours. So this is of course not up to time scale, but here you see how losses go down. These are losses with respect of something started, but I don't think we need it anymore. So let me briefly just say a few things. I was using so-called time marching, so we have some Tmax up to which I train this neural network, and only when results are good enough, I move to the next Tmax. So this number will grow up. These are the numbers of the time when I am trying to compare results of classical computation, here it is in white, with computation of my neural network. So when I start this video, you will see that these things are getting better and better. This is time t equals 1 and t equals 1.48. So let's start and see how it plays. So here our t is getting to 0.34, so at some point we should see that this thing has more or less coincided with what we expect. Tmax is still growing, so the next one should be this one. So at some point we will see that results start more or less coinciding. And here this will be the last one, that's t equals 1.48. And here we have some estimation of the real part of the wave function. So here are just probabilities, so that's psi times psi star, and this is the wave function. Okay, so we have trained that. I guess I can start inference. Yes, it starts a little bit better. So here is here is the potential I used for training. These are psi times psi. The white thing is psi times psi star for the classical method, so that's our ground truth. The red thing is basically what is predicted by our neural network. The other two things, here is a blue line, maybe not clearly seen. That's the ground truth for the real part of the psi function, and another orange thing is the real part of the psi function predicted by the neural network. So let me just show you how that evolves in time. So here you see the particle, it gets closer to the barrier and it starts interacting with the barrier. So at some point you might see that we have certain differences. Here is some difference between our ground truth and whatever our network predicts. Here is some small difference, but anyway they are more or less coinciding. Well, the main problem of this method is that it uses a lot of different fine-tuning, and at the end of the day it works only with one potential. That is definitely not good. So split operator method, that is basically our ground truth. So it's mathematically exact. We have seen the formulae, they work pretty well, but we have to perform that on a grid, so we have to discretize our time and space. We cannot skip any step with this method, so I cannot just demand calculate me 1 second in the future. I have to take some very small steps and calculate everything, and it's only forward. The pins, they are mesh free, so after I trained my neural network, I just request give me 1 second in the future, it gives me. So no need to wait for that. They have ability to solve the inverse problems. I will show you a demo with an inverse problem. So we can try to estimate the potential by given wave function. That is pretty interesting physical problem as well. But they require pretty complicated architectural hacks, and the forward version of the pin is, let's say, pretty useless, actually. But let's check the inverse version of the pin. So the forward problem, we give potential, we give some initial psi function, we want to compute psi. The inverse problem, that is vastly harder for the classical methods, but they work much better with pins, is given some sparse measurements. So I have psi function measured at some points and at some times, and I want to reconstruct the potential V. This looks way pretty reasonable as the physical problem, because we have some physical methods that can supply us at least some of this information. So like cold atom imaging or attosecond spectroscopy, just recent Nobel Prize, or electron holography or something different. And anyway, if we are sending some particles into something physical and we are getting them back scattered, that's basically the problem. So I can measure some quantum state of that scattered particles, and I would really like to somehow assess what can be the potential inside of that thing that I sent particles into. So here are some classical approaches to these problems. To this problem, I will not get into any of those. I just want to mention that, of course, there are some classical approaches, but we are today in for approach with neural network. So we will do that. So we will try to force our neural network to learn potential V. And with this potential, we can try to propagate with our classical method the psi function, look what we get, the predicted wave, compare that to what we have measured, so we have some measured data, and then we perform our gradient descent step. So we use the fact that our classical thing is basically our classical predictor is differentiable. We use the fact that all neural networks are differentiable, and we basically use all these parts as some sort of complicated loss function for our neural network that has to predict our learnable potential. Okay, that's too much of details. Let's look nice pictures. Let's perform some inverse tomography. Here it is. Good. First of all, I will define some potential, and our neural network will have to guess that potential. So I just draw it, and we will simulate some psi function at some time steps, and then we will force neural network to learn this potential, so to guess it basing only on that data of quantum state of the particle. So let's try with this simple thing, and then okay. So here it is. This is basically learning just now, interactively learning. So here is the blue thing is the potential predicted by neural network. This thing is hidden potential, so the one that I have drawn. And you see that they get closer and closer and closer. And these are predicted psi functions. So if I change, if I look back in time, you see that this psi function is predicted pretty well. And well, we guess, I guess we see that potential was predicted pretty good as well. Okay, let's try, let me restart this demo, and let's try giving to that network something more complicated. So why not? So let me once again draw some potential. So let it be something like this. And let's check what happens. So here we have, once again, we started training. So here we see how neural network is trying to approximate the potential. Once again, it doesn't see the real potential. It tries to guess it only basing on how good the predicted psi function coincides with measured psi function. So here we have. So this is basically, once again, it has pretty good, looks pretty good compared to what we had drawn. So this is the inverse problem. I can go once again back and forth in time and show you that here we have pretty good coincidence between the target psi function and the predicted psi function. Okay. Okay, let me start this one. Good, and getting pretty quickly forward. The last method I want to show you, that's so-called Fourier neural operators. This one is useful in a case we want to predict the psi function itself. So the previous case I tried with spins was pretty useless because I used just one potential, and whenever I will have some different potential, I will need to train everything from scratch. This idea comes to the fact, so why are we trying to approximate the psi function itself by given data? Why don't we try to learn an operator? So we can give it a potential, some initial psi function, and timestamp t, and we want to get the psi function as a result. So we basically want to approximate the time evolution operator. And if we manage to do that, that's pretty good, because we can basically instantly travel in time as far as we wish. And we can do that with different potentials. So we are not locked in with one potential and so on. So here we have to change our point of view a little bit. So first of all, we have to get to the Fourier space. So to approximate that operator, we have to get from our usual space to the Fourier space, and that's basically mostly connected to the kinetic operators that will be definitely present, because we may have zero potential, but we cannot have like no kinetic energies. That would be pretty strange. So at the end of the day, we are trying to construct something that looks like some Green's function. So our neural network will try to approximate something that will, let's say, look like the Green's function, and we will feed some data into that G, and we will get our psi at some timestamp t and space position x. The good news is that after we transport to the Fourier space, if we have some sort of translational invariance, we can treat our convolution just as the multiplication. That's really great. And the integration into physical space, that will be just a pointwise multiplication to Fourier space. So getting everything that together, we create the spectral convolutional layers that we will use in this neural network. If you look at this layer, it basically, how do I say that? This upper part, it mimics the classical method that we used to calculate our psi function after delta t. So you see, once again, we have some potential, so we do something with potential. We do Fourier transformation. Here we multiply by some matrix R. In that classical case, that was e to the p and so on. And here we do inverse Fourier, and here we get out. The lower part, that's some sort of kick from the potential once again. If we look at these closer, let me find it. This is pretty similar to the truncated Dyson series. So basically what we do with this neural network is in some sense on par with performing these sort of series. So we are performing like propagating free particle and then scattering it. So if I return to this image, this upper leg, that's basically the propagation of the free particle between scatterings, and this lower part that brings in the potential, that's basically the scatter. So in some sense, this layer can be reinterpreted this way. And then we put the results further. Okay, so if we skip all the boring part, so of course we add certain conditions. So we want to integrate some physics into training of this stuff, because I just have lumped some. I guess I have just collected 5 layers of that, but whatever they will give me, who knows? So we want some. We want our predictions to be more or less comparable to some classical estimations. We want some conservation of the probability, so there's always particles always somewhere. We want some high frequency fidelity and so on. And after we train all of that, okay, here is the training demo. If it starts, I will just briefly describe how the training process looks like, and then I will show the results of this training. So I have this network pre-trained. Once again, it takes some time, not 12 hours, but a bit too much. Here is the training process. So here you see how it goes. So this is the loss function. So that's the function we are trying to minimize. So here it is. It basically encapsulates well everything that we want some psi functions to coincide, predicted, and ground truth that certain physical laws should be correct. Here you see some random potential. So I was training this neural network on different random potentials that I have constructed as some Gaussian mixture model of up to 10 Gaussians. So I took different normal distributions and I just added them together with different weights and got some potentials. And here is the predicted some part, let's say real parts of the psi function and psi times psi 0 predicted with the neural network and with some classical method. And if we wait long enough, we will see that this loss goes down and these predictions are starting to coincide better and better and better. Of course, I will not make you wait all the time. I have a pre-trained network already here, so I will just start it, and after it starts, so here it is, we will just play around with this neural network, and that will basically conclude what I want. Okay, so here I have placed some potential. So this is just a simple potential barrier. Here we see the particle propagating, and once again we see the value that we have obtained by classical methods in white line. We see value predicted by this neural network with this red line, and we see the real part of the psi function. Once again, the ground truth in blue and predicted in orange. So we can see that, of course, they do not perfectly coincide. Maybe if I trained a little bit more, they will coincide better, but they still coincide pretty reasonably. And what is interesting here, to get the result for classical method, I have to calculate each time step from time equals 0 to time equals, let's say, 2. With this neural network, I don't need that. I just say I want in time equals 2, and it will get me the result with the same amount of work as it will get me for time equals 1 or 0.5 or whatever. So there is no background process. And it works, I want to show you, it works pretty reasonable. So let's try once again drawing something, some pretty random barrier with potential well after this barrier, and let's try to simulate the propagation. And here we see once again, so now the particle starts interacting with the barrier. With this, there are some small discrepancies between predicted information, between predicted data and calculated with classical method. But once again, what's interesting, I can use any potential, I just hand drawn it, so it's not hard coded anywhere or something like that. So you can ask me for different potential, I can draw different potential. But anyway, it predicts to some reasonable, with some reasonable certainty, the wave function that the particle will have at certain time step and certain position. Okay, I guess that's basically everything I wanted to say. So we have considered two different methods, starting from classic and ending with FNO. The main idea of FNO is that it works very well. It gives us instant result. Well, but we have to train it once, but for a long time. It's really good. Well, the rest we have seen. I guess, yeah, that's it.
Thank you very much, and I think we have questions. Please, somebody.
We have a lot of questions. The second part was really impressive, and I think you better should start from the second part and then explain
How it works.
But you can get a better coincidence with better prediction.
For
improve your prediction with larger database of how many. So you take some initial condition for C function and then some different potential.
Yes.
And how many?
How many steps I trained? Ooh, it's a bit hard to say, but this network wasn't trained for very long. So I think it may get really better if I train it for some longer time and give it some much more diverse potentials. Because this was just for demonstration, so I used just simple potentials constructed from Gaussian functions, and up to 10 of them, I guess, up to 10 Gaussians. Only a few layers in the network, so we can make it much bigger. And the bigger I make this network, the more we take basically that summons in the Dyson series, so it should get better and better with that. And of course, if we train longer with more diverse potentials, I think we can get much better. So yeah, so this is just some sort of result for demo, so I didn't try to make it some really.
So only one comment that the inverse scattering problem is the problem of decays, and I think that for physics in nuclear physicists in nuclear physics, it still is rather interesting.
We can probably make few lectures only on some classical methods.
To propose them,
Thank you very much. Volodymyr already used the word impressive. For me, it was also illuminated. So we have our own illuminator. Yes, the second part. Sorry, I skipped the first part. If I may, 2 or 3 questions. The first one is very trivial. I guess on one of the first slides, if you would there be any? You don't need to go there. Would be there any benefit if, when you substitute the exponential factor with the full Hamiltonian t plus t, you write half of b times t times minus half. If you split this process, say 1/3 half t, 1/3 half t, and would there be any benefit for the precision?
I should say I didn't check that. Well, this approximation is basically checked pretty straightforward. So we just transform exponents into the series, multiply them, and we see that what we get up to the 3rd order coincides with the perfect one. I'm afraid I can't perform that in my mind, but I guess I will find maybe.
That method of Japanese
Suzuki Trotter, I guess,
and they exactly split it into 3.
Yeah, they split into 3 terms, but I don't think that maybe we can split in a different way and get
delta t
to the 5th, for example.
Maybe. Okay. Then the first movies you have shown, they remind me very much the propagation of solitons. I don't know which boundary conditions you have used in your simulations, but it looks like perfect soliton without any energy dissipation, and even the interaction with the barriers. It reminds me that if the kinetic energy of the soliton is less than the energy stored in the barrier, then it propagates, interacts a little bit inside, only phase changes, and then restores its initial form and probably can be back and forth. Is there behind any nonlinearity in your program?
No, I used just simple Schrödinger equation, just with potential v that does not depend on anything except coordinate.
Right.
Yeah, so that's all that we
But
have.
and you use Gaussian
Barrier?
barrier.
Yes, of course.
Okay, but you also plot some more complicated. And the last question. We can have
Yes, we have a lot of questions, but we are here.
I get that method with Suzuki trotter, it works even with Gross-Pitaevsky. I can't be sure, but I think I saw something like that. So even in the case we have a little bit non-trivial, let's say, potential with some additional things, but it still can work there. So I guess I saw some works that when people were working even with Gross-Pitaevsky. So I guess we can make even a step further, but I didn't went so far for
That's
this
really
presentation.
fascinating. And again, almost coming back to last comment of Volodymyr Ivanovich, this inverse scattering problem obviously is important not only for the nuclear physics, but for non-linear. So the problem is, of course, to find the potential for the Lux spare. But probably with your method, you can play much more easily than with analytical. So
Well, maybe yes, maybe.
maybe-
I guess that the real world application may be more complicated than whatever I did for this presentation, because maybe I overused some information. Maybe, so I suppose that we may not have enough information about the whole wave function and so on, but I think we can overcome that with some larger networks, with some long training and so on. So I guess it may be done. So if I didn't check works in that direction, but I think we can do something.
Yeah, that's fascinating.